All right, everybody. So I wanted to talk us through the 3N, Newton's third law, and universal gravitation, this linearization problem. Now, linearization problems always kind of have the same general format. You're always going to start with a set of numbers, set of data that they give you. Whether they tell you to or not, you're going to need to use whatever situation and what they're asking about to come up with an equation that's going to guide your thinking. That has to happen. Actually, this part has to happen before you do your kind of numbers adjustment, because without this part, you don't know what to do. Now, in this particular worksheet, they just told you to do things, but I'll tell you why they told us to do those things. And then you have to graph things in order to get a straight line. And then you figure something out based on the question. Okay? So let's get started. Student is given the following set of orbital data for some of Jupiter's moons and is asked to use the data to determine the mass of Jupiter. Assume that these orbits and moons are circular, okay? So I'm going to jump past that information real quick and say, write an algebraic expression for the gravitational force between Jupiter and one of its moons. It says an expression for gravitational force, GMM over R squared is the one I would probably use. Use your expression from part A and the assumption of circular orbits to derive an equation for the orbital period t of a moon as a function of its orbital radius. So we want an expression for orbital period. Okay. So I'm going to start with F net C equals MAC. I'm going to go to F net C equals mv squared over r. I'm going to do a couple things in this step. I'm going to say what provides my F net C is the force of gravity. So GM over r squared equals little m v squared over r. My m's are going to cancel, my r's are going to cancel, so let me just gm over r equals v squared. I'm going to plug in that v is equal to 2 pi r over the period. And let me, okay. I'm not going to finish in the number of steps they gave me, but that's okay. So t squared is equal to 4 pi r cubed over g big M. All right. Which quantities should be graphed to yield a straight line whose slope could be used to determine the mass of Jupiter. Now this is the mass of Jupiter because this is the big thing, right? This is the big thing. And the problem said that there's Jupiter and there's many moons that are each orbiting Jupiter. So first, we have to look at what information they gave us in the chart that we're able to work with. They gave us information about period. They gave us information about radius. Therefore, I want to use the period and I want to use the radius somehow. So I'm going to graph t squared and r cubed, but the question is, where should I graph them? And I like to have it set up in this kind of format right here because that allows me to say set it up kind of with a y equals mx plus b situation. And I've got no plus b right here. So I would say that t squared is on my y-axis. R cubed is going to be on my x-axis. So mark that in, t squared on the y-axis, r cubed on the x-axis. Okay. This, after part C, is when we're actually qualified now to go back up to our data table and say, okay, that's why I want period squared, because of this. And because of this, that the radius cubed, that's why I'm going to do meters cubed. Okay. Last thing I'm going to mention doing here is let's just try to make sense of this, because this is, I did period squared and I did radius cubed, and all my radius cubes came out with times 10 to the 30th. So it's easy for me to see that 1.4 is my smallest number and 8.2 is my biggest number. When I'm looking at the periods, though, it can be a little bit trickier, because 4.3, 2.5 times 10 to the 14th times 10 to the 15th. So what I might recommend doing, and as long as you're watching this video, I'm just going to have you do it, is we're going to move the decimal place over by 1. So if I turn this into 16 times 10 to the 14th and 25 times 10 to the 14th, that'll make this read a little bit easier. 4.3 to 6.2, 6.2 to 16, 16 to 25. All right. Plus, being on the same field of times 10 to the 14th is going to make our graphing a lot easier. But now that we've got that, let's actually go ahead and see what our next step is, which I imagine is going to be the graphing. Oh yeah, sure enough. This is when they actually told us to do the table. Up until then, we were just being hasty. So we've decided to put period squared on our y-axis and radius cubed on our x-axis. I think I'm probably going to need to take a picture of my data points so that I can graph them. Oh, I could just do this. So let's do it. On my x-axis is 1.4 times 10 to the 30th, so 1.2, 1.4, 1.6, 1.8, 2. Okay, so yeah, 1.2, 1.4. And that goes along with 4.3. Okay. And then 2.0 and 6.2, 6.2. Oh yeah, actually they noticed that it's times 10 to the 14th. Okay. And 5.0 with 16 and 8.2 with 25. So now we draw our line of best fit. Probably do something like that. Exact lines of best fit will vary. That's okay. Even if you're doing this with me, the way you draw your line of best fit will vary, and that's okay. Some things that I do want to mention about this graph that were pre-filled in for you that won't be pre-filled in on a test is, first of all, the label on your y-axis. You don't have to write it out in words. If you just say t squared, that's fine. But I like that they included the fact, so to simplify their graph, they didn't write 5 times 10 to the 14th, 10 times 10 to the 14th. They could, but it's messy. What's better to do is what they did. Right? 1, 2, 3, 4, 5. 5, 10, 15, 20, that's fine. And then in the axes, say times 10 to the 14th. Now that's a separate thing than the units, which you also need to write. The units for period is seconds, and so for period squared is seconds squared. You have to make sure to do that. There are always points on a linearization question on the AP test for getting the units correct. Now, I'm excited because they made a mistake. Do you see what it is yet? I like that they said radius cubed. I like that they acknowledged the times 10 to the 30th down here. But they done goofed, Aaron. This should say meters cubed. So we got him on that one. Rank the magnitudes. Sorry. 2 identical probes are sent to study one of Jupiter's moons. Probe A is in geosynchronous orbit around the moon, while probe B rests on the surface of the moon and rotates with the moon. Rank the magnitudes of the following gravitational forces from least to greatest. If 2 or more of the quantities are the same, say so clearly. Oh, this is just a bunch of Newton's third law questions. Okay. So I'm going to pretty much say I don't care about that at the moment. The things you can do when you're the teacher. It's pretty nice. Not gonna lie. It's not a very good square, but it's happening, so deal with it. Cool. Why would I make okay, sorry. I'm gonna make those white. Style, fill, white, stroke, white. Style, white, stroke, white. Okay. So typically, the last question in a thing like this goes hand in hand with the question they asked you. They said, whose line could be used to determine the mass of Jupiter? And then they would say, determine the mass of Jupiter. Determine the mass of Jupiter. And how would we do that? Well, it would come back to this. Come back to what we did up here. Now, that's super messy. So I'm going to clean that up. And then I'm going to copy it. Okay. Okay. Well, we said that that's on our y-axis. We said that r cubed is on our x-axis, which means that this is the slope. Now, conveniently, the mass of Jupiter is contained within the slope. So if we can move things around, t squared over r cubed equals 4 pi squared over gmj. So if I take my rise divided by my run, of this line, I can get a number that will be helpful in figuring out the slope. So let's do that real quick. First question I'm going to ask you is, should I just, use this point right here and this point right here? The answer is a strong no, absolutely not. You spend all this time making a line of best fit. Use it. Find points that show up nicely on your line of best fit and use them. So let's see. This is 6 times 10 to the 14th up to 19 times 10 to the 14th. So I've risen by 13 times 10 to the 14th. I started at 1.8 times 10 to the 30th, and I'm ending at 6.2 times 10 to the 30th. That one's harder for me to do in my head. 4.2, 4.4 times 10 to the 30th. So my rise over run is 13 times 10 to the 14th. 13 times 10 to the 14th divided by 4.4 times 10 to the 30th. E14 divided by 4.4 E30. This is where using the E is super helpful. If you don't use the E, you really have to make sure you use parentheses around everything that you do. So this comes up to be 2.9 times 10 to the negative 16th equals, I'm going to kind of skip this middle step, 4 pi squared over GMJ. Let's rearrange things now. Bring that up, bring that under. I guess technically that's a cross multiply. So let's say MJ is equal to 4 pi squared over G times 2.9 times 10 to the 16th. So I'm going to type into my calculator. Let's see. 4 pi squared divided by parentheses 6.67 E negative 11 times 2.9 E 16 end parentheses, enter. I think something went wrong. Oh, ha 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 ha. Okay, so I'll communicate what I did. I got the mass as 0.0002 kilograms. Now, does that feel right for the mass of Jupiter? No. So, first thing, I go back and I check my powers. 10 to the positive 16th when it was supposed to be 10 to the negative 16th. So let me fix that. That feels better. 2.04 times 10 to the 27th kilograms. That seems more like the mass of Jupiter. All right, so earlier in the class period, so technically we're done, smiley face. But earlier in the class period, I mentioned that I wanted you to do this problem 2 times, one with period, and then once with frequency. And I'm going to show you that actually it's not more work. Actually, isn't bad at all. So let's pretend we were given frequency instead of given period. Well, the units on frequency are hertz or 1 over seconds. And so we would go through all this stuff and we would get to this step, and then we go, oh man, we're supposed to use frequency instead of period. And so we would write in, oh yeah, okay, period is 1 divided by frequency. So we would make a substitution right here, and we'd get 1 divided by frequency squared in place of the period. So let me rewrite my whole equation. Kind of running out of space. I'll go over here. 1 over frequency squared is equal to 4 pi squared. Oh yeah, look at how sloppy I was. 4 pi squared r cubed over GMJ. Okay. So if they gave me frequency, which in this circumstance now I have been given frequency, I would still line everything up the same way. Y equals mx plus b. Still no b. I would just, it's odd to say, but I would put 1 over frequency squared on one of my axes. And you know what? That's fine. I would put r cubed on one of my axes. Though I do like writing it kind of off to the side, so that I don't have to have it quite as snaky. So I would go back up to my table. I'd say, okay, I need to do frequency not only squared, but 1 divided by frequency squared. And so I want you to do that right now with this number. Take this number, get out a calculator, say 1 divided by parentheses 4.8 e negative 8 end parentheses to the second. And you know what you get? You get that number. And when you do this one, you're going to get, whoa, that number. So we're going to go through everything. All the numbers are going to be the same. All the numbers are going to be the same. All that would be different is that when you get to this right here, you would say 1 divided by the frequency squared times 10 to the 14th in 1. Oh, well, let's double check. When we do 1 divided by the frequency, which has units of 1 divided by seconds, squared, we end up with seconds squared. So actually, it's not a problem at all. It's still in units of seconds squared. Not a problem. Let me show you one more thing. And then we would go through and we would solve it the same way. Everything would be great. Sometimes this equation visually just looks a little bit different, so you might get thrown off. So let me rearrange this, pretend as if it's the very first time we're doing it. Maybe we don't like that the 1 over f squared is currently by itself, and I'd rather put, I don't know how to say that. Just give me a second. Maybe I just want to get r by itself. So r cubed is GMJ all over 4 pi squared frequency squared. Now in this case, the math is still going to be all the same. I'm still going to want to end up graphing r cubed on an axis and 1 over f squared on a different axis. Sometimes it's just harder to visualize, though, that r cubed GMJ 4 pi squared 1 over f squared if I do this, then I would do r cubed on my y-axis, 1 over f squared on my x-axis, and then this would be my slope. Now, it's possible that you look at this and you say, whoa, 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 whoa. Last time, we had radius on our x-axis and, you know, the time thing on my y-axis. That's completely backwards now. How can this be? How is our slope going to be useful? Like, aren't we going to get the opposite answer if we have things flipped? And the answer is yes, we're going to get the opposite slope, but you'll also notice our equation is also opposite. Like that part says gmj over 4 pi squared, where it used to say 4 pi squared over gmj. So yes, things are flipped, but everything has flipped, so it'll all work out. Sorry this video got long. Have a great rest of your day, and good luck on the test.